Can you guys hear me? Perfect. All right, guys, welcome to my talk, Bootstrapping Payloads One Game at a Time. My name is Royce. I'm a malware developer, vulnerability researcher. The GitHub link for the repository is right there. I'll show it back in a little bit towards the end as well. One of the POCs is up there right now. But let's get started. Also, I'm going to try to get us out a little bit early. Hopefully get you guys seats at the closing ceremony. They're pretty good. And we can go from there. All right, so what is this talk? As kind of the agenda, we'll go through what is this, some games and goals, 4 different proof of concepts, and we'll finish off from there. All right, some terms for today really quick. These are terms for today. They're not overarching terms. They're not explicitly correct as well. But for today, this is how we're going to use them. We're going to talk about state machines. For us, it's going to be just taking states to data. For us, it will be mainly bits and or bytes. We're talking about rejection sampling. Rejection sampling for us is just going to be no's and yes. We're going to talk about winners and losers and states of a board. A lot of times if we have a winner, we'll keep it as a yes. As a loser, we'll keep it as a no. Anything else, we're just going to get rid of it. For us, that'll be rejection sampling. A validator will be the combination of both. So when combining those two, we'll talk about validators and what that looks like. And then we'll talk about seeds. Seeds will be pretty common in some of these proof of concepts and some of the work that we'll be talking about. All a seed for us today will be, we'll take a seed, we'll fit that into gameplay. Through some gameplay, we'll get a specific state. From that state, we'll get a target byte. We can rebuild a type of rainbow table, or we can plug in a rainbow table to get our generation of seeds from this. Also talk about bit baiting, and not on electrical engineering perspective, but software bit baiting. And for us, all today bit baiting will be mean is a binary semaphore. We'll use it in that terminology. All right, so synopsis, kind of the overview of what this is. For states, for us, from a malware perspective, an offensive security research perspective, states generally don't look like obvious malware. You can think of a state of a tic-tac-toe board, state of a chess game. These shouldn't equate directly to our payload. We're going to try to make it do as such. Focus today is initial access, and really kind of the goal for this, for me, from my perspective lately, has been ransomware testing. If I get initial access with my ransomware payload ready to run, well, initial access a lot of times is all I really need if we've embedded pretty deep. So initial access is really the focus of today. We'll also talk about security through obscurity, and while it's not the most effective way to do security, from an offensive security standpoint, if I get initial access, and it can be a simple way to do so, maybe that's enough, and we'll talk about and really look at that, why that is. We'll also talk about games and recursion and how many recursions we can do. Maybe we need to play games a lot. Maybe we need to do a lot of execution styles or a lot of types of executions. How that works out for us and how we can generate our payloads, embed into our loaders and do our work. We'll talk about that and take a look at this. And proxying. Proxying is going to be kind of the overarching theme for a lot of this. How many proxying, how many actions can we take or do to get to our end state or goal for that initial access? Another way to describe this or boil this down to is really we're talking about data at rest and data in transit. What should we look like? What should we change? And how can we look non-malicious or as benign as possible? I don't have the answer to this question. There is a lot of possibilities you can approach this in. There's a lot of different routes people take. Some really creative ones, some fantastic ones are out there. But here are some of my ideas when I approach this problem, and it really kind of started as a seed of an idea. All right, so picture this. You have a client machine on your machine. Tic-tac-toe is running, Connect 4 is running, you let these go, maybe some dice are rolling, maybe somebody's playing chess, and all of a sudden from this perspective, a payload emerges from here. My meme didn't load. From a payload emerges from your game state. It could be Microsoft Solitaire as well. Maybe Microsoft Solitaire is playing on your client, and all of a sudden a payload has emerged from this state. But we're going to be talking about this and taking this idea and running it from here. What I want to make a point of is it doesn't have to be games. Games, to me, I thought was a really good way to demonstrate this. They have a preset amount of rules, preset amount of moves. It's easy to play in these states and use these and really easy to translate these. We're going to be using an idea of code books, not electronic code books, but classic cryptographic code books. We have a preset idea of preset states, ways we can translate this on the back end. Well, that's a way maybe we can turn what our payload would be in a benign state into a malicious state from here. So join me on a journey. Really what this was, this idea really embedded was, I do a lot of covert communications channel research. I really love that work, and I do a lot of malware development. Really, I was like, well, what if we take games and we can get past the defensive stack? That can be whatever EDR of choice, how many layers you have on your environment, really looking for that initial access point. My idea is, well, if we can use state machines, and really it started from the idea of using weird machines or binaries already on the target system. Can we make it do interesting things and point it to a payload from doing an action it's not supposed to, but can we do that ourselves and control these states? So the through line, this will be the overarching line for today. This will be the goal for all the proof of concepts. We start with a state machine, and state machines, I think, are a fantastic way to talk about this because, again, they can be preset, and it doesn't have to be a move. It doesn't have to be data, or it has to be data. It doesn't have to be a move. It doesn't have to be an action, but it could be data itself. And if the data looks benign, how can we translate that into some way, shape, or form? We're going to take this state machine. We're going to extract it. We're going to extract some real meaningful value from this. We're going to stream that somewhere. Once we stream it, we need to rebuild it. So we need to decode what we set as benign states, and we can execute that from there. And that's an up to you kind of decision for your OPSEC. Today, I'm going to be using Linux for demonstration purposes. This rolls into, you can use this idea for any operating system. It's operating system agnostic. I like working in Linux. Linux was the operating system of choice for me today. All right, so just a quick warning or correlation or things I need to say. Nothing here is FUD. The focus of today is shifting correlation. I'm not giving you a loader that's going to work immediately on the fly. If you combine these techniques and tactics, that's up to you. And really, if you choose to use anything for malicious purposes, your shenanigans, your problems, I have to say this. All right, let's start with proof of concept one. Let's begin. We're going to start from the starting point where this idea came from and the problems that come with this. And really going to kind of walk through the development process from here. All right, so the idea started from here. What if we use tic-tac-toe to make our payloads? And how does that look like? We start on target. We're on target already. We're going to play tic-tac-toe. And from playing tic-tac-toe, can we get our payload to emerge? We can do this an amount of times up to our choice, and we'll talk about better ways to do this than that choice I did. And we really can focus on recursion at this point and how many recursions or how many tic-tac-toe games can we play to get our payload from here. And problems that come with this. If we're playing a lot of tic-tac-toe, that should look suspicious on your environment. So the through line for tic-tac-toe, we're going to take these tic-tac-toe states, extract those states, extract the state of tic-tac-toe. We're going to stream those states somewhere, set them off. We need to decode and rebuild that and execute, and you can do this again and again and again. I choose to do that, and then you can point to a final execution from here. All right, so what this looks like. So tic-tac-toe, right, we want to code our payload. We're going to use rejection sampling to do this. We're going to mine for symbols. So we start with a payload of choice, payload agnostic. We're going to start with this mining process. If I have a payload, a certain amount of bytes, I'm going to say, hey, look, we're going to translate this into tic-tac-toe games. A winner for us will be a 1, a loser will be a 0, and anything that's a draw will be discarded. That is chaff. Chaff can be chosen. The amount of chaff you use is really up to you. After we have these states and we're ready to send them off, we'll have to decode these somewhere, and that'll be up to your load or your execution style. We'll decode and rebuild those bytes in that stage. For me, I chose to do it in memory. You do not have to. Again, Linux is the choice for today. However you choose to use your loader is up to you. From here, we've rebuilt ourselves, our tic-tac-toe game. We've decoded, and now we're in memory. We're going to execute, and for me and my choice, we're going to repeat for a certain amount of depth. How many times do you want to play tic-tac-toe? How many times do you want to rebuild yourself? And at some point, we're going to collapse this down. We're going to fork and parent. We're going to do PID hopping. And I thought that would be a fun way to do it. If anybody's familiar with PID hopping, you can immediately think of pros and cons that come with this. But some interesting ideas came from that for me. What this looks like in a coding perspective, right? We play tic-tac-toe, we're mining for those states. You can do this offline. For this example, I was doing it on target, playing tic-tac-toe over and over and over again. Payload is sent to the tic-tac-toe player in some way, shape, or form. Use your imagination from here. We play, we rebuild, we play, we rebuild. Embedded with it in the full stage is the payload. So at some point, our final execution, we crash, we reject, we do something. Our payload now executes. For me, it was just a simple reverse shell, and we go from here. Well, I want to point out one of the problems that comes with this, I added a perf top screenshot from here, is CPU usage. Anytime we do mining on target, we're loud, right? We're using CPU usage which we shouldn't be. And if we're doing a lot of mining, that's a lot of CPU usage. It gets really heavy. We want to avoid this. And we started doing this offline in the later versions of this. But I wanted to point that out for prosperity reasons. Some obvious problems that came up from this proof of concept in my mind. PID hopping sucks, but it has a caveat to this. I want to put an asterisk there. If you have a program or a process that's unknown to you and a PID hops again and again and again, it rebuilds itself, new child does this again, kills the parent, new child kills the parent, that's very abnormal. That's really abnormal behavior, but we want to talk about from EDR perspective. As a reminder, EDRs do scoring, right? They're taking in context. While we can actually use this as a pivot into when we want to talk about scope, right? I might have 2 days for scope-wise to get my malware to detonate and get past your loader, or my loader to get past your EDR. If I'm a bad actor, though, I'm absolutely happy to leave this running for 47 days. So if all you have is a program that's running and killing itself and doing it again and again and again for 47 days, while that'll look abnormal, will that be loud enough for your enterprise to see, oh, this is really, really bad? Or will you see, this is a really weird process that just keeps rebuilding itself, but it deletes its past and it's just doing benign actions? Will your EDR after 47, 50, 60, 100 days eventually let it go? And when the final detonation happens, will it be able to tie in that initial execution from when the game started to when the payload executes? And I would advise you just to try that in your environment. How long can something go and to lose that tracking on it? CPU usage time, and this is a common problem many of us come into. So if I have something that goes really, really fast, CPU usage goes up, time goes down, right? Again, we need to talk about bad actors. Remember, time it's a different factor at this point. If I want to let something run for a really long period of time, well, maybe I can mine symbols really, really slow. It's something that needs to be considered in this portion, and something I considered as well. So when I start to build these things out, it's really what knobs do I want to turn and how fast do I want to go up from here. Low symbol rate. So tic-tac-toe, we should know, has 9 spaces on the board. For this, I was just taking winners and losers. It's a really inefficient way to do this, actually. Instead, what we could do is set up a token or a byte on the back end or the front end and say, hey, look, the other 8 spaces on this board, well, that's data we can translate to. And so we should do that. But again, a problem that came up from when we do rejection sampling, start looking away. It's not winners and losers. It's not single states. Think of a chess game. How many chess moves can be played at one period? Think of it as a factorial. How much does that go up over time? Can that explode too fast? Can you fit your payload into that curve? Play around with different games. We'll talk about a different game than I use, actually. It was a picture earlier. That's a more efficient way to do this than tic-tac-toe. And execution. So we're talking about initial execution. This focus on this process, this proof of concept, was not worried about execution so much, but more about just hiding the data before it becomes executed. So if you ever use a tactic specifically like the one I just showed, you still have to bring your own loader. And that's always a problem that we have to deal with. Custom loader development, while I enjoy, I think, and it's really, really fun, not everybody does. So while a fun project, not particularly feasible, so let's talk about something that is. So something a little more common, and we'll talk about C2s and a protocol. So let's take this idea, see if we can make a protocol now. And what we want, our goal really is, can we have payload bytes that are never in plain text over the wire, and they're carried as states? Can we send gain states over and decode that on the back end, on the target machine, and really turn that into a payload from there? Through line for this, we have game states. We send that. We extract those game states from some way, shape, or form. Right? We need to have value from these game states. So we still have to extract that value, stream it somewhere. For us, will be into a loader. The loader will rebuild this. And for us, we're just going to be a .h file. We're going to use it as just a simple header file that you can throw into any loader. It'll take the decoded states, or take the encoded states, and decode those itself. And then it can decode or execute. Choice is up to you for OSTEC purposes. You can keep it there, you can pipe it off, choice is up to you. Once you can execute your C2 agent, and you can have communications back to your server. A little bit smaller version of this, C2, it's going to send those game data. For us, it's going to be states of tic-tac-toe, encoded states of that. Connect 4 games, chess states, coin flips, and dice rolls. From here, those states get sent into our loader. The loader will do something with it. For us, it'll just do a straight decode to execution style. We'll detonate. From here, we get connection back to our C2. So just sending our game states to our loader, the loader will recreate our payload. Protocol core, what the protocol actually looks like. On the left, you can see it encapsulated. For us, the idea really is just take your payload, slice it up in a bunch of small chunks, encode these bits into game state packets, send those packets off that hold the bits that can be decoded into your payload. Again, we're payload agnostic from here. When you do custom protocol developments, I recommend always do a session key or a handshake. How cryptographically secure is up to you. And this is a good point I would like to make, is if we're focusing on initial execution, if you reverse engineer and do analysis on the loader and the payload, et cetera, nice job, fantastic, drinks on me, but I got my detonation. I walked away with what I wanted from here. My actions were able to be taken at this point. And the payload has to do its own work, but again, we got our initial execution stage. Handshake session key, fixed size packets. You can do dynamically sized packets. It's a lot more complicated, but again, we want these packets to look like game states. And we can do this in two different ways, which we'll talk about. Each packet will say what it is. Are we a chess game? Are we Connect 4? Are we tic-tac-toe, etc.? And most packets will be chaffed, at least in the version I did. Connect 4 is the real data for us. Connect 4 is a really nice way to do this. There's a lot of spaces on a Connect 4 game. If you encode and use that size of the board, how many rows and columns you decide to use can really be set to how many bits you want to send over and or bytes. The choice is up to you from there. We're going to decode via PIC-C header, and I'm going to make a point, and we're going to talk about PIC-C in a little bit. You'll see a lot of this. PIC-C is position-independent code. From a malware development perspective, we see a lot more of this than assembly development these days. I love working in assembly, but we see a lot more PIC-C if we ever want to make loaders or payloads or C2s. Everybody likes that. Everybody likes working with that, and we'll talk about why. Not my favorite, but it is what it is these days. And output from here, after we do decoding, we get our protocol. Once we get enough packets, right now we rebuild into our payload. So we're sending data, we say what size we are, right? How many bits have we encoded, and what engine ID or what game style are we using for this. Oh man, my right side didn't load. All right. Right side, we'll imagine it's there. Left side is binary. At the bottom is really just the actions that are being taken. The right side was JSON. Looks very similar to the left side. Left side is binary, but we'll just talk about the JSON style, which looks very, very similar. Take up your payload, chop it up a bunch of times, right? Get JSON style game states, right? A lot of games work via JSON. Send JSON files over to your payload. Payload takes over all the data it wants from these JSON states and decodes that into viable data. You can do encoding, you can do encryption, the choice is up to you. While we're not cryptographically secure at this point, at least the encoding style I use, it really depends how you want to interact, either escaping sandbox or how much action you want to take to make the workload increase. A lot of what we want to talk about, a lot of the focus really is we're making it harder for analysts, right? We want to increase work time. While it's going to be easy to do this on the back end, if work time increases enough, well, hopefully by then we've had initial execution at this point. So chop that up into JSON files, send it over, decode at some point, decode and execute from here. On the bottom, I just want to show, right, it's a simple loader style, right? We're just using everything's in memory, a lot of mem maps. If you want to talk about IOCs, tons of mem maps and executions is really, really loud. So again, you should bring your own loader if you want to edit this and choose to use this in your own ways. So why PIC-C? And really the question boils down to, do you like to write shellcode and custom C2 agents in assembly? Do you like to write your payloads like that? And it's really a question every offensive developer should ask. Some love it, some do, I do, but not everybody does. It's a lot easier to work in PIC-C and inline assembly, so you see a lot of that happen these days. A couple repos down below, Crack Spider Stardust really popularized this. The PIC library by Silent Warble, it's a great collection of all of these, and he keeps adding to them all the time. And then I wanted to make a point on the Pico implant. It's, I would say, a newer version of PIC-C tools and libraries. I think it's going to keep continuing in this style, in this version, and people are already working on really interesting ideas in this. And so I would make the bet now it will stay like this and continue in this way. So operational takeaways from a protocol. It's a stager. So we're staging, we're proxying our data somewhere for you to use. Again, how many layers, or can we get even a single layer deep our payload, right? You continue with your proxying status. How much do you need to do? This will increase complexity. So how much complexity you are willing to incur on your operation, it's a conversation you need to have with yourself and your team. And really is how much time do you have? More complexity, it means a lot more dev work on the back end and where you're doing work. But if it's enough to get away with what you need, well then again, as a bad actor, if I just need it to work, that's all I need at the end of the day. Chaff, again, anytime you use protocol, anytime you use any type of staging or encoding, specifically rejection sampling, you'll have your yeses and nos, the states you like, the states you don't, but you'll have ones in between. How you deal with that is up to you, and how much of that is what you want. Again, multi-stage chain, or just how much staging do you want to do? And if you want to use Pixie, it's your call. Are you an assembly bespoke dev? Blue team side, correlation, right? If you have a bunch of packets coming in, going straight somewhere, and eventually executing, that's pretty loud. So again, staging-wise and proxying, your choice. Heartbeats, as we know, C2 agents and C2s use a heartbeat. Introduce jitter, introduce timing, put it to sleep, find a way to reactivate it. That's a way to get under and away from this heartbeat detection. And you can reverse engineer this easily, right? This is not encrypted, it's encoded. So there's no it's not cryptographically sound. It's really easy to reverse this on the back end. You can choose to encrypt this. Nothing says you can't, but now we introduce entropy. And the conversation of, is entropy loud enough to get me popped, really depends on the EDR and the defense stack you're using. Some would say yes, some would say no. It just depends on your environment and what your EDR is choosing to look at that day. Decode loops and memory transitions. So anytime you do decoding on target, that's loud, right? You're doing mathematical operations within one program many times. If that's not normal, that can get you popped. Nothing says you can't branch out and add this logic to other programs, use various threads, kill threads, etc. Again, it comes back to that proxying problem, what you want to do. And again, memory transitions, bring your own loader, however you want to handle that, and that actual detonation, that's a choice. So bring your own loader, right? I kept saying that, right? Well, why are we even here, right? We're talking initial execution. We're not doing that. Well, let's do it. So I said initial execution. Let's talk about a loader, right? And what we're going to be doing is we're going to use several different techniques on this. We're going to use file locks as an IPC mechanism. We'll talk about seeds, tables, using those two together, decoding those via game states, and using the DWARF mechanism and hijacking for the GCC hijacking to take advantage of control flow and really get our payload to start doing something interesting from here. Again, Linux for the demonstration purposes, how this will look from a loader perspective. All right, the through line for this, we're going to use Connect4 pretty heavily for this. So we're going to mine and encode. We're going to mine and encode our game states. From here, we'll get our game states, just match up to your payload. We're going to do some mining process, right? If I have a byte, I need to give that a numerical value. We'll look at that, what it looks like next. Extract seeds from here. Again, seeds are that recipe number. If I throw that number into a Connect4 game, well, when that Connect4 game runs, it will decode into the byte I want, staging and proxying from this. We're going to use an IPC proxy stream. You can use file locking and bit baiting together. I'll talk more about that on the next slide as well. We'll rebuild via these Connect4 states. So as Connect4 runs, it has done the decoding process for us for our byte. This will decode into a Connect4 and get our byte and etc. We're going through this process to get our payload back. We're going to do some funky execution from here. Again, control flow hijacking. Idea comes from this, really. Let's play a lot of Connect4 games, right? Connect4 will error out at some point. It's a really poorly written Connect4 game. And from this, you get your payload. So we'll hold seeds, IO Covert comms, get Connect4 after that, and we'll hijack from there. So details and slides. So sender's going to pre-compute mine seeds, right? It's going to do some math. It's going to do some math that you really can choose to do this. Throw in your payload, right? I think I threw in like a 500 byte reverse shell, just added some extra fluff to it to make it a little bit larger. We could pre-compute mine seeds from this, do some mining. We need to turn every byte into a value from here. Once we have those mined seeds and we have a list of seeds, it's how you encode those or encapsulate those is up to you. And how you send those off, again, is really a choice of flavor. From here, we're going to do IPC bit baiting. So we'll use file locks. File locks will talk back and forth to each other. We'll lock sections of a temporary file that we create and or so choose. If you use a non-used temporary file, fantastic. You can control the file locks on that file. You can map those out into bits. That encodes into data and going from there. Keep in mind, right, we'll use a lot of file locks. We do a lot of file locks already on Linux. If you list all your file locks happening, a lot's happening all the time. So this becomes a conversation of security through obscurity. Problem is, and how you want it, there's several ways to do this, but if you want to offset this into several processes, great. If your file locks are talking back and forth the same process over and over and over again, why is this process file locking constantly all the time on this same shared file? That would be your IOC. Receiver is going to take these mind states. After it does the file locking operations on target, it's going to take these seeds, what it's received. It's going to take these seeds, it's going to run connect4. Connect4 will do the decoding for us. We run these connect4 games. We get our states. We can translate those states into bytes. Our bytes have been rebuilt, and we now have our payload. We'll hijack this. So we're running a process, our loader is running. We're going to use GCC's exception handling. This is found in libgccs. We're going to use the unwind force unwind engine from here. We're going to use DWARF, the DWARF process in Linux. The simplest way to explain DWARF map or DWARF mapping is really, if you have a process that crashes, DWARF's going to try to map it back out to the last safest state. It's going to say, hey, we crashed here. We're either going to go up and we're going to terminate this process, or we're going to walk the stack all the way up and find a safe state, crash our process here, and continue execution for a clean stack. We're going to hijack this. We're going to take that. We're going to point the rip at our payload. We're going to execute our payload from here. So we're just doing exception handling, and we're using, it's not quite VEH, if you're familiar with that, more just control flow than anything. So, and then the rip is our payload we can execute at that stage. Some more details in slide. This one's kind of heavy. On the left, though, is just a quick, good look at what this looks like visually. The miner takes your payload that you fit in. Let's say we have byte 90. For some reason, maybe that translates to 14023. That's our seed. That numerical value is a seed that we'll have. Our sender is going to have this list of seeds. It's going to send and map out these lists of seeds via file locks. On the receiving end, after all these file locks, it accepts these. It's now going to have this list of numbers. From here, we're going to run connect4 per each seed. Each seed will now decode into target memory, which will decode into our byte, our 90 back over. We do our control flow hijacking. For us, we'll have a shell. All right, so a little bit about file locking and bit baiting, what this kind of looks like. Right, it's really a presence or an absence of a file lock. Right, think again back as a semaphore, as an on or off. Right, think of it more as an atomic operation, and can we match these up and can we talk back and forth with each other? We're using on and off and acts basically. So we need to synchronize. We need them to talk to each other. Sender and receiver have to be able to see each other. We synchronize here. Sender's going to set 32 locks plus 2. The 2 is the first one. Say, hey, we're on. This is our file. Second one is going to be used for the receiver as an acknowledgement. If it's on or off, we've acknowledged that we can see the file locks. Right? We're now going to set 32 locks in the file as a map. It doesn't have to be 32. I did it arbitrarily. You can do as much as you want. 32 bits on and off right after those two maps out to data. You have an unsigned 32 integer that you can use. From here, it's up to you if you want to keep it alive. We can talk about consistent file as persistent data, where if this is constantly going back and forth, we have data on the target that's never on disk, and we just keep it going between file locks. You can keep it alive. You can keep it there as long as you want. Your IOC, again, will be lots and lots of file locks, but it can be a persistent storage way if you so choose, just very syscall heavy, and it can be resource intensive if you do it way too fast. But again, you're doing mappings and readings. You can read and not read the map at your timing as you so choose. The execution vector, what this looks like, right? So calls and jumps are often hooked, especially in programs. If we start doing some random jumps and calls, that can get you kind of popped, and we don't like that. For the loader style, still memmap reconstruction. Again, a lot of memory operations. If you do a lot of those really, really fast, and you stay consistently in memory the whole time, that's allowed. But we like that, right? Anytime we touch disk, again, they can see that, but a lot of memory is loud. So we need to find a balance that we're happy with. For me, I kept it simple. I just did a lot of mem maps, right? If I've gotten to this far, hopefully the mem maps work. If they see that, well, then we know we can change our loader from here. But again, maybe we'll be blocked off at this point. It really comes at OPSEC and what are your operational costs and what you're willing to accept. Control flow, so we invoke that unwind force unwind. We walk up the stack from there. Once we've invoked that, we're going to intercept that walk before it gets a state of termination. And once a terminator game, I thought it was very bad. We're going to grab that, say, don't go up to termination. Then we're going to point it to inline, our shellcode, that's inline assembly. Pivot to rip to that, when our payload will be on the heap. Do a heap execution from there. Now we have our payload at this point. That is none of my pictures. Fantastic. Okay, all right. Let's come back here and let's talk about how that would look like. So, code-wise, it looks very simple, right? We have connect4 running on the targets, right? Connect4 is running, it's decoding, right? As we're sending the seeds over, seeds get over, next seed, next seed. I was sending via batches, so 10 seeds, 10 seeds, 10 seeds, 10 seeds to do the decoding process at that point. You can do less or more, right? How much decoding you want to do at once, again, is how much mathematical operations you decide to do. Too much is too much, right? And too little makes you slow. Again, it's this idea of how much time do you have to get that execution style. Connect 4 is running, right? I added a GUI. You don't need a GUI from there. Connect 4 runs. Connect 4 game runs, the game fills up, right? You have bytes, and we can go from there and we build our payload. What I really wanted to show in the next slide, which isn't there, is the Connect 4 game had far more than 4 connected, and you had up to 6, right? So if your game state doesn't look normal, we really have to incur, well, at some point we'll see why is Connect 4 doing 7 games in a row or 7 stacks in a row. That's not Connect 4 at all. So we need to decide, do we want to look normal enough, and how much normal should we be looking? It's an interesting question, right? Because what is truly benign? So you and I, Connect 4 is Connect 4 to a computer that thinks it's running a program that we define as Connect 4. It might not know this, right? The rules are what we preset. So what can you get away with is a question that you have to answer and decide. All right. Well, okay, my pictures are not there. All right, fantastic. Okay, so we did our execution, we did our loader, right? We've done our loading process. Let's talk about custom packing. This is a popular thing to do. Problems that come with packing, encoding, encryption, etc., really is entropy, right? If you have a lot of entropy and you have an encrypted blob on system, that is particularly loud. There's a lot of ways to do this and bypass this. Some of the projects I'll talk about later, actually towards the end, that others have done. But if I can make my payload look normal, right, that's what we want at the end of the day. But we always want our payload smaller. Like size is really important, i.e. working in assembly or working in PIC-C. If I can keep things small, I can start to put it in smaller places. The smaller I go, the more room I have to work with. So we want to see, can we do this in a way that's relatively unique, not really detected, and we can make new IOCs every day by doing just some simple custom encoding, some custom packing to really make ourselves fit where we want to. The through line for this, right, and kind of the final recap for the final through line is we're going to start using dictionaries now. We're really going to lean into tokens. So we're going to take a dictionary of our payload, and we're going to build out these tokens. We'll talk about what the tokens look like in the next slide, but we're going to turn every payload byte into a token. We're going to have an index of these. What do these tokens map out to, and can we connect these at the back end for us to rebuild this into our payload? We'll use these into D20 states. We're going to just roll dices, right? We're going to roll dices. Each dice number, and in a section with our index, will map out to a byte of our payload, multiple proxying and multiple coding. The goal with this, though, was turning these tokens and using this dictionary to make our payload smaller, right? Our payload plus our decoder should be smaller than our payload would have been. So we want to keep everything really, really small. And can we do that with decoding logic? That's a hard problem to solve. Decoding logic just adds extra size, but if we can get both of them over the wire, we're doing our job right. We get these dice 20 states, list of roles. I'll output a dice 20 text file. Hopefully it shows up in the picture in 2 slides. We'll find out. We'll stream those D20 rolls. Once we have those dice 20 rolls, we're going to unpack. And all the unpacking and coding we've done, we're just going to do it backwards. Go backwards, you can verify, I like to. You can use your custom hashing of your choice, multiple ways to do that. And then you can execute. Again, this is a packer and compression. This is not a loader. So you still have to bring your own loader once you've unpacked and encapsulated your payload into one. The overview of this. So we take our template. This is just your payload, right? Code of choice, right? We have bytes from here. We're going to turn that into a dictionary plus F tokens. So every time we have empty space, or we have relatively the same bytes, or we are looking for standardization, we turn these into tokens, and we want these into small tokens. These tokens plus our dictionary will be the offsets of the bytes that we use for our payload. We're going to take those tokens plus our index. We're going to turn those tokens into digits, tokenize that, add that, and make those numbers. Turn those numbers are small enough that we can fit a 5-bit pack. Now we have digits into a 5-bit stream, and now we have our binary. Our binary has all of this. It's our decoder plus our payload that's been packed and compressed. Right, so your pack digits, your dictionary attached, your offsets have been listed out using the tokens to find those offsets. I use an FNV 1A32 hash. I find it very easy to work with, but I have a habit of checking things with SHA-256. I don't know why. And then we just do it backwards. So things line up, right? We have our 5-bit pack. That goes your 5-bit pack. right? Dictionary compress, tokens from here, everything matches up and goes backwards. And we just do it backwards until we get what we've done. We're doing our mathematical operations just in reverse, right? And the idea at the end of it is we have our payload has been rebuilt cleanly, we can verify it, we have our output, and we go from here, right? So it's just encoding and custom packing to get this all together, but we need to make sure we've done it right, obviously, or otherwise you're gonna have a batch payload. Fantastic, that's always good news. Okay, so all that looked like was CLI text, right? And the CLI text, what that looks like is just what the values want, right? We'll see there's a list of dice 20 rolls. Those dice 20 rolls, just simply the numbers in the list. From there, we also have just running. We can see the sizes, and unfortunately, you're gonna have to take my word for it at this point. We'll have our payload, a set custom size. Our custom size will be smaller than the full decoded and the full decryption process and payload on the back end. We've just made ourselves smaller. That was our goal, right? We made ourselves smaller and we're good to go from here, right? Ways to make this quieter. So there's a lot of verification I've done and a lot of just making sure everything works up and lines up well. Remove all of that, remove any output, don't give it custom dice rolls. What we want to look like is just a list of integers, right? We're a list of integers for some reason, shape, or form, right? We package and stream those out again and again and again. You have to take that decoding process in exactly the same backwards fashion to get your payload on the back end. That's what we wanted. Your defense stack, your EDR, your sandbox has to know what the encoding style is, and if it's a custom style, is it able to do that? Is it able to figure out the logic that this happened in, and can it manually do it in reverse? If not, it just thinks you've sent it a list of numbers. What is it going to do with that? Some are better than others at this, right? Not all EDRs are built the same. Some will try to figure it out, and I would encourage you to see, is yours able to figure that out after a couple mathematical operations and can't figure out which ones were done if you just send it a stream of integers. Perfect, beautiful. All right, so why does this really matter at the end of the day? Your payload looks benign, right? That's our end goal. We're not raw embedded, we're not raw payload bytes. There's other ways to do this. We'll talk about Jargon if anybody's familiar with Red Team's work or Red Siege's work. Jargon's a great way to do this. There's other encoding mechanisms as well. Lots of different ways. This has been on IPv6 addresses, MAC addresses, etc., and embed those into your loader. We're staging this. So this is another way to stage and just a list of integers that somehow we decode and decrypt on the back end to turn this into your payload. We're compressed by design. We're not like gzip or unzip or any of the other ones. We're not 7-zip. We're not following a classical pattern of compression. Also, our entropy is lower, right? Once our entropy is lower, we're also more benign. If we're not a classical compression style, we might not be recognized as a compression style, right? And we can live with that, and that's something we want. Again, the goal is initial execution. Again, in-memory reconstruction, right? Flavor of the choice or choice of flavor. How you choose to rebuild and where you choose to rebuild it is up to you. My advice always is if you have to touch disk, do it with purpose. Again, the end goal of this was just a smaller artifact. Some similar projects related to this. So for the protocol, it makes most sense to talk about LOLC2, if anybody's familiar with that. Just legitimate binaries and legitimate programs that people have encoded C2 operations into. We've talked about states, and the idea with states, again, it can be anything, right? However you choose to decode and encode your program and encode your data is up to you. You can, if you go to LOLC2, you'll see Zoom, Microsoft Teams, I think I've seen Counter-Strike. There's, I think, really anything under the sun. The idea remains the same. Can I map out particular actions to data? Again, that classical codebook idea. If I am able to decode those actions some way, shape, or form, maybe even embed what I'm sending, well, now we have a custom encoding style that just is a normal, and it's really just up to us what it's going to be looking like. From an IOSD perspective, you're going to have to look at just what does this look like to you all the time? What are these custom encoding styles? What are these actions being mapped out? That becomes difficult if we do any legitimate binary, any legitimate program to custom out or to map out the custom actions that can be malicious. Fantastic, and that's why people use this for C2 agents. And if you want to get into C2 development, it's a fantastic way to start and take a look at. Jargon, I like Jargon a lot. I like the work they did with this. They built onto this, and other people have done similar things with this. Their encoding style was take a byte, map it, and build a dictionary first. That byte, I think they did actually ASCII characters mapped out to a word, and each word is now they just embed a list of words into their loader, right? And the jargon implant decodes those words into the bytes they were supposed to be. Another way to do a custom encoding as well. You can do this multiple times. Nothing says it's a one-off, and it's not a one-off shot. If it works for you, great. And again, if you only have 2 days to get past EDR, right? If it works, fantastic. You got tests, you got access, you can do your operations from here. Again, if I'm a bad actor, sure, initial execution is still my goal. I'm not limited to 1 or 2 days to get it to work immediately. I can take my time, right? And I would take all the time I could and have a lot of fun with it on the back end as well, right? If I can do multiple ways to do this, multiple proxying, multiple staging, of course I'm gonna make it as complicated as possible for defenders. And again, my goal is to make analysts and the defenders' work take really long time. Again, if you decode it and you get it on the back end after I've already detonated my ransomware, fantastic. My ransomware is already executed. Your files have been encrypted. So what can we do to find these custom encoding styles, mathematical operations, and really get payloads first from here? The third one I found really, really fascinating. And from a covert channels perspective, this is a great way to partake a type of data and translate it. I don't play Minecraft. If you do, fantastic. This is a Minecraft mod. And what it is in Minecraft, the characters are bits of their pixels. What they did in rendering distance from the server side and client side, if you're in rendering distance, your pixels are going to translate really, really fast. Send your payloads through those skins that they had. The blocks change really, really fast. The render, as you render those skins, you can translate that into data. They use it as a covert communication style. Think about in invasive environments where you really want to try to talk to somebody where maybe they're getting watched really tightly. Doesn't have to be Minecraft, but we can start looking at things that get either rendered locally or within a program itself. What is the server and the client seeing particularly? So I thought it was a fantastic project. If you play Minecraft, go check it out. Not me, but again, I want to throw that in there. I thought it was very fascinating. All right, so summary. So state machines, they can be used as shift detection, right? That is our goal. The goal is to shift detection and shift correlation, right? As long as we look benign enough and we don't look malicious enough, we're doing our job right, and that's really what we wanted to get away from this. And rejection sampling has pros and cons. There's other ways to do verification and combine this to become a better validator. If you're taking wins and losses, I think that's a bad idea. What kind of states can you take, and how much data can you encode at once that looks valid, and can you take that and add chaff and et cetera to make a valid way to rebuild your payload? Recursion can work with caveats. So again, PID hopping, I think sucks, but again, if you do it over 100 days, 1,000 days, is it enough? Choice is up to you. Test it with what you think. But recursion can be local. So again, if we do decoding on disk or on the target, if we do it too loud, we're too loud, right? If we do it too fast, we're too fast. But maybe we can slow it down and maybe we can proxy this off to do another thing and another action and to decode that into something else, right? Send this off to other programs, right? Send it off somewhere else. Maybe do it within a browser. Maybe do it off of Microsoft Solitaire, etc. How you choose to send data around and proxy it and encode it in various states is up to you, but I would encourage you to check out what you can do and what you can find in this space. Multi-layer proxy obfuscation, again, the goal is for raising costs, right? Just the goal is to raise costs and raise that time to find, right? If the cost is too high, all right, and we can talk about sandboxing and escaping from here and evasion, but if the cost is high enough, hopefully we've been let through and hopefully we can do what we want on the back end. That is the goal. And again, it doesn't have to be games. However, I thought games was a great way to show this, right? They have preset rules and they're simple rules. If you can map out all the rules and actions of something to data, well, you've now found a way to do covert communication. That's a covert communication channel. You decide to build around that. Fantastic. Publish it as a C2. I love to play around with it, right? So again, it doesn't have to be games. Thank you. That's it. That's all I got for you. That's all I really wanted to show you. Also, graduate May. I'm looking for a job. Please. Thank you. Awesome. And that's it. That's all I got. Yeah. Any questions? Perfect.
The purpose of with games and state machine is
Yes.
So for your proof of concept, the third one, is when you're using DWARF, is there any chance for data loss prevention? Like you lose a game state there?
Yes. Yes, and if you don't, it's more if you don't walk up and you don't walk up correctly, right? As we walk up that stack, you can overshoot it really easily, you can lose it, and et cetera, right? As the operations are happening, if something heavy happens really, really fast, maybe it wants to take space away from you, right? We're basically doing stack manipulation at that point. How you interact with it and control it and or freeze it or isolate it, it's kind of up to you. But you can do it within the programs. Remember, in Linux, a program, again, Linux specific for this, programs work within their own memory space. So if you can keep within that memory space and not leak out and control the pointer at that point, you're in a good spot. Does that answer your question? Perfect. All right, any other questions? Perfect. Thank you, everybody. That's it. Hope everybody had a good conference. Thanks for coming to CactusCon, and that's it. That's all I got for you. Thanks, guys.